So with the theoretical background of step impedance filters, where we have seen inductor is represented by a high impedance line whose electrical length can be obtained in terms of R, like the system impedance, and the normalized reactance and the impedance value that we have chosen as a high impedance value. Similarly, a capacitor, a lumped capacitor, can be represented as a line which is having a low impedance line. So for a microstrip line, if we say, so high impedance line represent a thinner variant. However, the so it's like microstrip, say suppose we have a microstrip and we have, this is the width of say first microstrip. So this is, say the width is W1, this is W2. So W1 is less than W2. Okay. So for especially for microwave, the microstrip lines, what happens? This line represent with the width which is less. So this is a high impedance with respect to this line. Okay. So this is a low impedance line. This is a high impedance line. So if we say in terms of Z01 would be greater than Z02. So the characteristic impedance of this line and characteristic impedance of this line. Okay. So with this theoretical background, so what we have seen in this step impedance line, so we can replace these lines with high impedance line and low impedance line to represent the lumped inductor and lumped capacitor. Okay, now we're gonna do one example to understand the concept little bit more. So I'm reading the problem for you and we'll write the key parameters on a board for this. So this problem says design a stepped impedance low pass filter. So the problem is specifically specifying we have to use the stepped impedance filter design, and they have also given us a one hint, so with the help of maximally flat response. So this is a Butterworth filter, and they have given a cutoff frequency of 2.5. So cutoff frequency, if it is given in hertz, so we need to say like this, is 2.5 gigahertz, and it is necessary to have more than 20 dB of insertion loss. So the PLR at the frequency they have given us as 4 gigahertz, it should be greater than or equals to 20 dB. Okay, and the system of impedance is given as the R naught is given as 50 ohm. So this is what we have given in the problem. This is the formulation that we have to use in order to have a filter design, a low pass filter design using the step impedance transmission line, step impedance method. And there is one more thing is given. So the maximum impedance that you can realize, Z high, it can go up to 120 ohm, and the smallest impedance you can implement till 20 ohm. So this is the information is given as far as the problem is concerned. Okay, so the first step of this problem, to solve this problem, so we have seen in previous cases as well, the first step is to calculate the order of the filter. Okay, so for calculating the order of the filter, we have standard expression, and we can also have a kind of we can derive that expression as well. So but I'm just writing straightforward 10 log of 10, 10 to the power PLR divided by 10 minus 1 divided by 2 into log of 10 omega upon omega c. So this is the expression that we have to use. So by solving this, we get some orders of something order 6, and this same order can also be calculated graphically. So you can refer Posar book, where they have plotted attenuation for different orders. So here is the PLR, say 20 dB and 30 dB. So you can just have what is the order of omega upon omega c here. So you can calculate the order graphically as well from that plot. So let's assume this is equals to, the order of the filter comes out to be 6 for obtaining isolation more than 20 dB in the stop band at frequency omega equals to 4 gigahertz. Okay, so let's assume this. The first step is this, to calculate the G parameters, right? So the first step then would be the G parameters. So G parameters for a maximally flat response with filter order 6, we can directly take from the book, or we can easily calculate also. So I'm just taking directly from the book because it's relatively easy, because we have seen how we can calculate these parameters from equations. Okay, so let's see what's the G0. G0 for the maximally flat response is 1, so as Gn plus 1. So Gn plus 1, which is, because order of the filter is 6, so it would be G7. This would also be equals to 1. Now G1. So G1, now I'm just taking as a reference from the book. So G1, so I'm writing very quickly, G1 is 0.517, G2 is 1.414, G3 is 1.932. Okay, now we know that these parameters are, so this G3 can be equals to G4, 1.932, they have symmetry. So G3, G5 would have equal to 1.414, so as G6 is equal to 0.517. Okay. However, you can calculate these parameters from very simple equation. We have discussed this, G equals to twice of sine of 2k minus 1 into pi divided by twice into n. So you can use this equation and you can calculate all the G parameters. So now what's the next step? So the next step would be to calculate these individual values. Okay, so let's say in this fashion, the section number, so the first section, okay, then the first section, if we consider this as inductor, so impedance ZH or Z low, and then what would be the beta Li. Okay, so the first section for a low pass filter would be an inductor and then capacitor, then inductor, then capacitor, then inductor and then capacitor. Okay, so let's count. Do we have 2, 3, 4, 6, 1, 2, 3, 4, 5, 6. So this would be G1, G2, G3, G4, G5 and G6. Okay. So right now, with this stepped impedance transformation, if we want to realize an inductor, so we need to use a high impedance line, which is 120 ohm. Okay. Now the beta Li for inductor we can calculate in terms of this expression. So this is gonna be L, which is basically a G1. So G1 is 0.517 multiplied by system impedance, which is 50, divided by ZH. So ZH is 120. So if we solve this, so you can solve this for me. Okay, I don't have a calculator right away. So we're gonna solve this later. So the second section. So the second section is a capacitor, which we're gonna realize through a low impedance line. So low impedance line in this problem is given as 20 ohm. And how we can calculate the beta L for this? So beta L would be calculated as CZL divided by R0. So C is our G2. This is G2. G2 is 1.414 into ZL. ZL is 20 divided by, we have R0 as 50. So this is the second. Now if we have a third section, which is G3. So G3 is inductor. So this is gonna be realized through a high impedance line, which is 120. And now we need to write for this again the beta Li, which is LR0. So L is for this G3 1.932 into R0. R0 is 50 divided by ZH, which is 120. Okay. Now I'm gonna bring calculator and I need to calculate these values. Now we need to understand, as these G parameters are having one symmetry, so as we have the symmetry in our rest parameter as well. So whatever is for 4, which would be equals to the third component here, right? So everything gonna be same. The fifth would be replaced by every 2 value, and the sixth value would be replaced by this row. Okay. So let me bring the calculator and calculate these. Okay, now I have my calculator in my hand, so let's calculate these quickly. 0.517 multiplied by 50 divided by 120. So this comes out to be, so if we multiply this, your value gonna become in radian, so we need to multiply it by 57.32 again to get a value in degrees. Okay, so this is gonna be value which is something like 11.8 degree. Okay, now the second thing is 1.414 multiplied by 20 divided by 50, 57.32. This comes out to be 32.4. Okay, and the next value would be 1.932 multiplied by 50 divided by 120, and we need to multiply this. This comes out to be 46.14 degree, and so as the other values we can calculate. So now what we have in our hand? We have the electrical lengths. Okay, we have electrical lengths, we have impedances, and we have like how many components are in our filter. So we can easily realize a filter with this set of calculated values. Okay, so let me draw a whole filter for you so that you can understand how each and every inductor and capacitor is being replaced with, sorry, I don't want to rub this right now. So yeah, okay. So our low pass filter would be something like this in lumped circuit element, right? Now, what is the equivalent stepped impedance filter? So we have a transmission line which is equals to Z0, and then we have a high impedance line. This is the microstrip. So this is Z high and this beta into L1, the electrical length, beta L1, and now we can put this as 11.8 degrees. Okay. Then we have a capacitive line, which is a low impedance line. So this is the low impedance line. Okay, so this is Z0. This is representing a capacitor. So this is 20 ohm and this high impedance line was 120 ohm. So the electrical length for this line is 32.4 degree. Okay. Then again we have an inductor with 120 ohm, and then we have again a capacitive line, like a low impedance line of characteristic impedance 20 ohm, and the electrical length for this line is 46.14 and the electrical length for this is equals to 32.4 degree, and then we need to continue with the same high impedance line, and then suddenly this gonna landed with a Z0. Okay, so this is 50 ohm. So this would be again 120 ohm and the electrical length is 11.8 degree. So this is the physical realization of stepped impedance based low pass filter. Okay, so here is the distributed diagram of a step impedance filter. So here we have a system impedance, then we replace this inductor with a high impedance line and again a capacitor with a low impedance line. So the impedance is decided at first stage. So what would be the maximum impedance we can realize? So we have taken 120 as a maximum realizable range of this. So it depends on various factors of microstrip line, the height of the permittivity of the substrate and all. So this is the procedure, and this is the final design of the filter. So the next step would be to take these values into any software, maybe a CST or ADS, and try to simulate this with a kind of given, say, some realistic values for the microstrip lines. So let's consider this microstrip is designed on FR4 substrate with certain epsilon r and 10 delta of this value and with certain substrate height, say 1.5 mm. So then try to see whether after doing these calculations, whether your filter comes out to be a low pass filter with a cutoff frequency around say 2.5 gigahertz, the cutoff frequency FC, and whether it is giving isolation at 4 gigahertz more than 20 dB or not. So that you need to check with your simulation studies. So thank you very much.